So I've mentioned hexadecimal a couple of times, right? Hexadecimal is base 16 notation. So each digit ranges from 0 to a possible maximum value of 15. Now, obviously, we don't have symbols for 10 and above because we're base 10 people. So to represent the larger hex digits, we use letters. And you've probably run into hexadecimal plenty in your life, right? So A is 10, B is 11, C is 12, and so on, right? So F is 15, the biggest hexadecimal digit. Right? Cool. But how? I thought this was a course on binary. Why are we talking about hexadecimal? Okay. What else has a range from 0 to 15? I already talked about it, right? Those 4-bit values that we were talking about for some of our simple examples, right? Unsigned 4-bit values range from 0 to 15. Right? Each byte is 8 bits. And each byte could be subdivided into 4-bit chunks. By the way, yes, we call them nibbles, right? So 8 bits is a byte, 4 bits is a nibble. Okay. That means that you can represent a byte, 8 bits, as 2 hex digits. And it's a lot more compact representation of a byte than having 8 ones and zeros, right? Instead of filling up, 8 places on your paper to represent a byte, we can just write down 2 hex digits to mean the same thing. So the reason hex comes up so much in our computing world is because it's just a compact way of representing an 8-bit byte. 2 hex digits represents 1 byte. Right? So I've got a byte here, right? You see what it is, 1010, 0111. Okay? And I want to represent that byte using hex. So we're going to break it up into 2 4-bit chunks, and we're going to attack each one separately. So first one. All right. That first 4 bits, right? It's an 8 and a 2, right? 8 plus 2 is 10. Now, 10 in hex notation is an A, right? That's the first thing after 9. Okay? So that's an A. That first nibble is an A. Okay, now the next 4 bits, right? That's a 7, right? 4 plus 2 plus 1, okay? And in hex, 7 is 7, right? It's just the number. Okay, so we only start using the letters when we get to 10 and above. All right, so instead of 1010, 0111, we can represent this byte as A7 in hex. And usually we hang a 0x on the front to indicate that we're talking about a hex number. Because, for example, if instead of 10, that first byte was a 9, right? It would appear as 97. And you don't know whether that's a decimal 97 or a hex 97. But boy, does it matter, right? 97 hex. Remember, this is the ones place, right? The 7 is the ones place. But now we're talking about base 16, right? So that A is in the 16s place. Right? So that A, 10, represents 10 16s. Right? So that's 160 in decimal, plus 7, 167. Right? All right, so that's how you convert binary to hex, right? You look at each nibble, right? You figure out what it is. Decimal is the easiest way to do it for us, and then write that as a hex digit. This is why hexadecimal is so common. It is a convenient, compact encoding of an 8-bit byte. And of course, we can go the other way, right? So here is how many bytes? Remember, 2 digits is a byte. So two digits, that's 1 byte. 2 digits, that's 2 bytes, 2 digits, that's 3 bytes, 2 digits, 4 bytes. So this is a 4-byte value represented in hex, right? Much more compact. But we can convert it back into binary. All you got to do is you got to just attack each digit separately. So 7 in binary, 0, 1, 1, 1. A in binary, well, it's 10, so 1, 0, 1, 0, an 8 plus a 2. And we can keep going. Hey, 1 is just 1, right? So 0, 0, 1, 0, 0, 1, sorry, 0, 0, 0, 1, 0, 0, 0, 1. Okay, those are the two ones. Then we've got C. Let's see, A is 10, B is 11, C is 12, right? So 12 and 10. So 8 and 4 is 12, 8 and 2, 10. And then a 7 and a 5, 1, 1, 1, 7, 0, 1, 0, 1 for 5. Okay, so it's easy to translate back and forth between hex and binary to hex, because you're just dealing with 4 bits at a time and translating them. Obviously, if I wanted to know what the heck this was in decimal, I would whip out my calculator. Right? So let's see, we're going to put this into hex mode. And I'm going to, right, so we'll go to hex mode. I'll type in 7A, 11CA, 75. So hex, it's that. Binary, it's what we just decoded. So this should match what we did here. But in decimal, it's 2 billion and some extra. So it's very easy to convert from binary to hex and hex to binary. As the numbers get bigger, you're definitely going to need a calculator, though, to convert this back into decimal. Now, so hexadecimal is base 16. You also sometimes hear about octal, although not so much anymore, right? So octal is base 8, right? So digits range from 0 to 7. That means we can use 3 bits to represent octal digits. And frankly, there's only ever one modern use case for this that I've ever seen, and that is Linux and Unix file permissions. So in Linux and Unix, we talk about read, write, and execute permissions, and they are literally represented in the internals of the file system as 3 bits, right? So read is the 4's bit, W is the 2's bit, and execute is the 1's bit, okay? So if you have permissions for the file owner, read, write, execute, like that's all 1s, and that's a 7. Then you have permissions for the group owner of the file. So the file may be owned by a group that's sharing that file, like software development, code kind of thing, right? So maybe the group owner only has read and execute permissions. So the 4's bit is set and the 1's bit is set. So as a decimal number, or really as an octal number, that's a 5, and the same for the everybody else group. If you're not the file owner or belong to the group that owns the file, then you're everybody else, and you might have read and execute permissions, and that would also be a 5. And so this is what we call the symbolic representation of the file permissions, the R, W, and X. And then the octal version is what we call the absolute mode of the file. And literally within the file metadata, these permissions are represented with these strings of 3 bits, which we can write in octal. Okay. So that's how permissions are stored in Linux and Unix internally. And so you'll hear Linux people saying the permissions bits on a file, because they literally are bits in the internal data structure. Okay, so that was a quick one, because I want you to now practice, you guessed it, converting things from binary to hex and back again. because, dealing with hex numbers is definitely something that you're going to be doing a lot in your life. So here's that ASCII encoding of binary is not scary, and it takes up a whole lot of space. What I want you to do is now translate these to the hex representation, which is a lot more compact. And then, hey, IP addresses, cool. And oops. And then have a little bit of fun with octal and Unix permissions, okay? All right. Let me just talk about some of the answers here a little bit. All right. Okay, so binary to hex encoding. I'm not going to do all of these, but let's take it for the first couple. All right, so again, you're going 4 bits at a time, right? So 0, 1, 0, 0. Well, that's the 4's place. Okay, so that one's a 4. And then 0, 0, 1, 0. Well, that's just 2, right? 4, 2. Next one, 4 plus 2 is 6. Right? And 8 and 1 is 9. And it just goes like that. Now, again, obviously I'm lazy, and I didn't do this by hand. Just like there are sites that convert ASCII to binary and vice versa, there are sites where you can literally cut and paste a bunch of binary values like this, and they will spit out the hex codes, right? Which is exactly what I did here. But what's important to recognize in all of this is that, we wasted all of this space with the binary encoding of these characters, but the hex encoding is, much more compact, less than half of the number of digits compared to the binary. So, this is why hex is popular, because no one wants to write out all those ones and zeros. Okay. If you were to look at a packet on the wire, like you dump it out in hex view of Wireshark or whatever, right? The IPv4 addresses are represented as a sequence of 4 bytes, actually what we call octets. So believe it or not, bytes were not always 8 bits. Back in the mists of time, there was some confusion about how many bits were going to be in a byte. And we gradually settled on 8 bits for reasons that I'll discuss actually in the next section. But in order to distinguish an 8-bit byte from a 6-bit byte or a 7-bit byte, or whatever the fancy took you, the term octet was introduced to mean an 8-bit byte, and networking literature still speaks of octets, just to be very specific about what they mean. So we talk about the 4 octets of a 32-bit IP address. All right, and so yeah, I mean, in hexadecimal, they're just represented as a sequence of bytes in hex, and then to decode them, you just take each byte by itself. So 0A, right? Okay, well, that's just 10. 0, 1 is 1, 0, 1 is 1, and 0A is 10. So 10.1.1.10, right? You just put the dots in between. This is where you start needing a calculator, right? I mean, C0, okay, so that is, okay, remember, A is 10, B is 11, C is 12. That is 12 16s. I can't do 12 times 16 in my head, but it ends up being 192. There's nothing in the ones place. So yeah, it's 192. And similarly, A8. Okay, so that's 10 16s. So 160 plus 8, so 168. 0A, well, that's just 10. And then 8 times 16 plus 9. See, 8 times 16, 128, right? Plus 9 is 137. Go me. All right, 10 16s plus 12. Okay, it's 172. 116 plus nothing. Well, that's 16. A 12. And then 6 16s plus 3. All right, 6 times 16, 96. Plus 3 is 99. So yeah, I mean, we can encode and decode IP addresses, IPv4 addresses, byte by byte. I mean, you could do it with a 128-bit IPv6 address as well, but just takes longer, right? Okay. And just because I'm a Unix guy, let's talk permissions. Okay, so this is a very common permissions vector. We use it often on, text files and things like that. So read, write, read, read. Okay, remember the read bit is 4 and the write bit is 2. So that's 6, 4, 4. So 711, going back the other way. So 7 means all the bits are on. Okay. So read, write, and execute for the first, which is the owner. And then 1 is just execute. So read, write, execute, and then execute, execute. So that is the, permissions there. If you don't live in a Linux universe, you're never going to see octal again in your life. It's just, we just don't use it anymore. Seemed like a good idea at the time. No. Okay. Question about using CyberChef to decode these, huh? I've never tried it in CyberChef, to be honest with you. I mean, there's got to be a way, right? Maybe during the next exercise, I'll sit down with CyberChef and try and figure out how to do the binary to hex conversion. That's an interesting question. I mean, I don't know the answer to this. So the question is, do you see octal in, for example, vehicle forensics? So embedded systems, I think, is a more general, like vehicles, drones, all of that, low-level embedded Internet of Things stuff. The answer is, I don't know. I don't do forensics on those platforms, but I could see why it's an open question, right? Because obviously, with embedded systems, you're trying to keep the information density as great as possible, and maybe you're trying to pack information into, like multiple fields into a single byte. So I don't know, you might be dealing with 3-bit values in octal. But I don't know, it's not a world I live in. Interesting though. So there was a question earlier that I punted, asking how to convert from binary values like um, our secret message to hex using CyberChef. And I was sure there was a way to do it. I just, needed to play around with it. So By the way, if you've never seen this before, this is CyberChef. CyberChef kicks ass. Okay, so CyberChef can help you with like all of your encoding and decoding needs, everything from simple stuff like base64 and lot13 and stuff like that to, well, pretty much any arbitrary thing. And you use it by putting together what are called recipes, right? So over here on the left-hand side, you've got all these different options and categories, and you can expand them, right? So, YARA rules and EXIF data and all these different encodings. What I'm using here for this is data formatting, right? So what you do is you take like, so I want, from binary, somewhere down in here. Oh yeah, here it is. So from binary, you would pick this up and you would drag it into the recipe area, which is what I did here, okay? And then the next part of the recipe is convert that binary to hex. So you go down here and you find 2 hex and you would drag it and drop it in here, right? And you can set parameters like, okay, the delimiters are going to be space and 8-bit bytes, and I want the hex output space delimited, and you can specify, a number of bytes per line, or set it to 0 and it'll just spit them out in a big long line. Okay, and then you put your input up here, and then you click bake, and you're done. And here's the answer, right? So yeah, CyberChef. So I'm a Linux guy and I do this this kind of crap with XXD and things like that. But honestly, CyberChef is what normal human beings use for all your encoding and decoding needs. CyberChef is really something that's worth learning. Maybe I'll do like a short presentation on CyberChef. Because there's a bit of a learning curve. But anyway, fool around with it because it's definitely something that will help you. You can just Google for CyberChef.